So I just showed you that empirically the likelihood will converge, but theoretically it can also be proved that EM algorithm would converge to a local maximum. So here's just the illustration of what happened, and a detailed explanation. This would require more knowledge about some of the inequalities that we haven't really covered yet. So here what you see is on the x dimension we have theta value. This is the parameter that we are after. On the y-axis we see the likelihood function. So this curve is the original likelihood function, right? So this one, and this is the one that we hope to maximize, and we hope to find a theta value at this point to maximize this. But in the case of mixture model, we cannot easily find an analytical solution to the problem. So we have to resolve a numerical algorithm, and EM algorithm is such an algorithm. It's a hill climb algorithm. That would mean you start with some random guess. Let's say you start from here, that's your starting point, and then you try to improve this by moving this to another point where you can have a higher likelihood. So that's the idea of hill climbing. And in the EM algorithm, the way we achieve this is to do two things. First, we'll fix a lower bound of likelihood function. So this is the lower bound, you can see here. And once we fit the lower bound, we can then maximize the lower bound. And of course, the reason why this works is because the lower bound is much easier to optimize. So we know our current guess is here, and by maximizing the lower bound, we'll move this point to the top, to here, right? And we can then map to the original likelihood function we find this point. Because it's a lower bound, we are guaranteed to improve this guess, right? Because we improve our lower bound, and then the original likelihood curve, which is above this lower bound, will definitely be improved as well, right? So we already know it's improving the lower bound. So we definitely improve this original likelihood function, which is above this lower bound. So in our example, the current guess is the parameter value given by the current generation. And then the next guess is the re-estimated parameter values. From this illustration, you can see the next guess is always better than the current guess, unless it has reached the maximum where it would be stuck there. So the two would be equal. So the E step is basically to compute this lower bound. And we don't directly just compute this likelihood function, but we compute the latent variable values, and these are basically a part of this lower bound. This helps determine the lower bound. The M step, on the other hand, is to maximize the lower bound. It allows us to move parameters to a new point. And that's why EM algorithm is guaranteed to converge to a local maximum. Now, as you can imagine, when we have many local maxima, we also have to repeat the EM algorithm multiple times in order to figure out which one is the actual global maximum. And this actually, in general, is a difficult problem in numerical optimization. So here, for example, had we started from here, then we gradually just climb up to this top. So that's not optimal. And we'd like to climb up all the way to here. So the only way to climb up to this here is to start from somewhere here or here, right? So in the EM algorithm, we generally would have to start from different points, or have some other way to determine a good initial starting point. To summarize, in this lecture, we introduced the EM algorithm. This is a general algorithm for computing maximum likelihood estimate of all kinds of mixture models. So not just for our simple mixture model. And it's a hill climbing algorithm, so can only converge to a local maximum, and it will depend on initial points. The general idea is that we will have two steps to improve the estimate of parameters. In the E step, we roughly are augmenting our data by predicting values of useful hidden variables that we would use to simplify the estimation. In our case, this is the distribution that has been used to generate the word. In the M step, then, we would exploit such augmented data, which would make it easier to estimate the distribution, to improve the estimate of parameters. Here, improve is guaranteed in terms of the likelihood function. Note that it's not necessary that we will have a stable converged parameter values, even though the likelihood function is ensured to increase. There are some properties that have to be satisfied in order for the parameters also to converge to some stable value. Now here, data augmentation is done probabilistically. That means we're not going to just say exactly what's the value of a hidden variable, but we're going to have a probability distribution over the possible values of these hidden variables. So this causes a split of counts of events probabilistically. And in our case, we'll split the word counts between the two distributions.